Hello, myself Dr. Rajesh S. Badigar, working as an assistant professor in the Department of Chemistry, JSS Arts, Science and Commerce College, Gokak. In this video, I would like to discuss about the derivation of an expression for frequency of lines in the spectrum of hydrogen and hydrogen-like ions. So that means, according to Bohr's model of an atom, the energy is liberated or energy is emitted when an electron jumps from higher energy level to lower energy level, and at the same time, if an electron jumps from lower energy level to higher energy level, there is an absorption of energy takes place. Now, the question comes, how to find out the frequency of radiation emitted when an electron jumps from higher energy level to lower energy level. For example, consider this one as an atom. Here, the electron which is present in N2 energy level, where its energy is E2, when it jumps to energy level N1, where its energy is E1, it will lose the energy in the form of radiation which are having specific frequency and wavelength. So now the question comes, how to find out the frequency of this emitted radiation or frequency of this spectral line in the spectrum. Now then the question comes, how this spectral line will appear in the hydrogen spectrum or any spectrum. This is very simple basic concept. For convenience, let us see. Whenever an electron jumps from higher energy level to lower energy level, it will emit radiation or it will lose energy in the form of radiation, and this radiation is having particular frequency or wavelength. So this radiation, emitted radiation, is allowed to absorb on a particular photographic film which will appear as a spectral line. That means each transition of an electron from higher energy level to lower energy level will appear as a spectral line. For example, in this case, the one electron which is present in the N2 level, when it jumps to lower energy level N1, it will emit radiation, and this radiation is allowed to absorb on a photographic film which will appear as a spectral line here. Now, if one more electron is present in the in another orbital or energy level, for example, if you consider here, if it jumps to next lower energy level, again it will also emit radiation, and this radiation, if you allow to absorb on a photographic film, it will also give one more spectral line. This is how spectral lines will appear on the spectrum. Now the question comes, how to find out the frequency of these spectral lines or frequency of this emitted radiation when an electron jumps from higher energy level to lower energy level. So today's discussion is the derivation of an expression for frequency of spectral lines in the spectrum of hydrogen and hydrogen-like ions. In this case, we have taken a particular example of a hydrogen atom. Okay. So for that, let us suppose an electron lying in the energy level N2, where its energy is E1. Suppose consider this electron, it is present in the N2 level, where its energy is E2. Now when it jumps to lower energy level N1, where its energy is E1. Now suppose the electron which is present in N2 level, where its energy is E2, when it jumps to lower energy level N1, where its energy N1, then it will lose energy in the form of radiation or it will emit radiation. Now the question comes, then the frequency of this emitted radiation is given by this relation. That means h nu is equal to E2 minus E1. That means the difference in the energy between these two energy levels. That means h nu is equal to E2 minus E1, or h nu is equal to delta E, where h is Planck's constant and nu is the frequency. So this relation can be written like this one. Nu is equal to 1 over h into E2 minus E1, or nu is equal to delta E divided by h. Call this one as a equation number 1. Here h is the Planck's constant, E the difference in the energy between the N2 and N1 energy level. Now here this difference in the energy would be emitted in the form of radiation of a specific frequency and hence a specific wavelength. Thus the emission spectrum of hydrogen would thus show a line at a frequency of emitted radiation. Further, this E2 and E1 are the energies of electron in the N2 and N1 energy level, and these can be calculated by using Bohr's energy relation, that is En is equal to minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n square h square. Now from this equation, that is energy of an electron in nth orbit or energy associated with the nth orbit, that is minus 2 pi square z square m e raised to 4 pi epsilon naught whole square n square h square, where z is the atomic number, m is the mass of the electron, e is the charge on the electron, and 4 pi epsilon naught whole square is the permittivity factor whose numerical value is 1.11264 into 10 raised to minus 10 coulombs per Newton per meter square. So and n is the number of orbit and h is the Planck's constant. From this equation 2, let us find out the value of energy associated with the this E2 and E1. That means find out the value of E2 and E1 from equation 2. Let us find out the value of E2, first one. E2, the energy of electron in N2 energy level. That means minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square. This one value is N2 square h square. Similarly, value of E1 is equal to minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n1 square h square. Now put the value of E2 and E1 in equation 1. Therefore, equation 1 becomes nu is equal to 1 by h. E2 means minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n2 square h square minus of 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n1 square h square. Okay. Similarly, that is 1 over h into minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n2 square h square. Here minus of minus will become plus. That means 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n1 square h square. Now take this one this side and minus will be this side. That is nu is equal to 1 over h 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n1 square h square minus this one minus 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square n2 square h square. Now which one is common factor here? Here common factor is 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught h square is the common factor. Therefore, take this one outside. 1 over h into 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square h square 1 over n1 square minus 1 over n2 square. Now this 1h and this h2 it will multiply. Therefore, nu is equal to 2 pi square therefore nu is equal to 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square h cube into 1 over n1 square minus 1 over n2 square. This is the equation or expression for frequency of lines or frequency of emitted radiation in the hydrogen spectrum. That means equation 3 is known as expression for the frequency of line in the hydrogen spectrum. Here the value of this factor, that means 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square h cube. Here z is atomic number and m is mass, e is electron, 4 pi epsilon naught value is the permittivity factor, and h is Planck's constant. If you put all these values, you will end up with the 3.2906 into 10 raised to 15. Therefore, nu is equal to 3.2906 into 10 raised to 15 into 1 over n1 square minus 1 over n2 square in terms of per second, or it is Hertz. This is the expression to calculate the, or this is the equation to calculate the frequency of emitted radiation when an electron jumps from higher energy level to lower energy level. This relation can be utilized. Okay. Now the same expression, that is frequency, this can be expressed in the form of or in terms of wave number also. That means equation 3 can be expressed in terms of wave number, that is nu bar. Now this equation 3 can be expressed in terms of wave number, that is wave number is equal to reciprocal of wavelength, that is equal to nu by c, where c is the velocity of light. Now this can be written like this one, 1 over c into nu. Now we know the value of nu from equation 3. Therefore, nu bar is equal to 1 over c into, write this equation, 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square h cube into 1 over n1 square minus 1 over n2 square. That is, you multiply here, that means 2 pi square z square m e raised to 4 divided by 4 pi epsilon naught whole square h cube c into 1 over n1 square minus 1 over n2 square. Here this factor is known as Rydberg constant. Rydberg constant, and its value is equal to 109,677.58 per centimeter, or 1.0967758 into 10 raised to 5 per centimeter, or 109.686 into 10 raised to 5 per meter. Therefore, this equation 4 can be written like this one. Nu bar is equal to R into 1 over n1 square minus 1 over n2 square. In terms of, this is the equation for, or equation number 5, you call this one as equation number 5. This is the thus nu bar is equal to R into 1 over n1 square minus 1 over n2 square, where R is the Rydberg constant and its value is 109,677.58 per centimeter, or 1.0967758 into 10 raised to 5 per meter per centimeter, or 109.67758 into 10 raised to 5 per meter. This is the expression to calculate the frequency of radiation emitted in terms of wave number when an electron jumps from higher energy level to lower energy level. Let us take one example. Calculate the frequency of spectral line in the emission spectrum of hydrogen when an electron jumps from fourth energy level to first energy level. So that means the electron which is present in the fourth energy level, when it jumps to first energy level, in that case energy is released in the form of radiation. Now we have to find out the frequency of that emitted radiation. So for that, here N1 value will be 1 and N2 value will be 4. Therefore, use the relation that is nu, that is frequency is equal to 3.290 into 10 raised to 15 divided by into 1 over N1 square into 1 minus 1 over N2 square. Here put the value of N1 and N2, or use this one. Nu is equal to 3.2906 into 10 raised to 15 1 over N1 square minus 1 over N2 square in terms of hertz of frequency. Use this relation. Here 3.2906 into 10 raised to 15 into 1 minus 1 over 16. So that will comes out 3.2906 into 10 raised to 15 by 16. That is the final result will be nu is equal to 3.0849 into 10 raised to 15 hertz. Let us take one more example. Calculate the frequency in terms of wave number, that is nu bar, when an electron jumps from second energy level to first energy level in the hydrogen spectrum. If you consider this one as a hydrogen spectrum, this is the first line. So that means when an electron jumps from second energy level to first energy level, so there will be formation of, there will be appearance of the spectral line. Now find out the spectral line frequency here. So for that we have to use the Rydberg equation. So this is also known as a Rydberg equation. So nu bar is equal to R into 1 over N1 square minus 1 over N2 square. Here R value we can take 109.686 into 10 raised to 5 per meter, or 109.67775 8 into 10 raised to 5 per meter. In some book they have mentioned this one also. So I will take this one. Okay. Here in this case N1 lower energy is N1 is equal to 1 and higher energy, that is N2 is equal to 2. Now put the value of N1 and N2 in Rydberg equation. That is nu bar is equal to 109.686 into 10 raised to 5 into 1 over 1 square minus 1 over 2 square. That is equal to 109.686 into 10 raised to 5 into 1 minus 1 over 1 4. Okay, therefore 109.686 into 10 raised to 5 into 3 by 4, that is 0.75. That will give you exactly the value 82.2645 into 10 raised to 5 per meter. This is the frequency of the spectral line present in the hydrogen spectrum.